Now we're going to look at some common polar curves. Now, so these are curves that are represented easily using polar coordinates, but not so easily using Cartesian coordinates. And they seem to have a lot of practical application. All right, so the first common polar curve that we're going to look at is called a limaçon. It's French, limaçon. It's of the form, all of them are going to be r equals something. R equals a plus b, and you can substitute cosine or sine in there. Now, just like when you were back in your mathematical childhood studying Cartesian curves, what did you do? Well, you noticed certain forms so that you already had a concept of what the curve was going to look like, and what that meant was you didn't have to plot a lot of points. That's what we're doing here, all right? So if it's of this form, it's a limaçon, and you're going to have some sort of concept of what it looks like. All right, well, the first case is if the absolute value of A is larger than the absolute value of B, then as it turns out, it doesn't go through the origin. So let's look at an example of that. R is equal to 2 plus cosine theta. We're going to plot a few points. Which angles theta am I going to look at? And the answer is, generally, I look at angles theta where cosine is either biggest, 0, or smallest. That is, most positive, 0, or most negative. Because I'm not going to plot 1,000 points. I don't have that kind of time, right? All right, and I know cosine is 1 at 0. It's 0 at pi halves. It's minus 1 at pi. It's back to 0 at 3 pi over 2. And at 2 pi, then it's back to 1 again. All right? So those are the angles that I chose, and then I'm going to put in the value for r, which of course is 2 plus cosine theta. So when theta is 0, r becomes 3. That gives me the point 3, 0. Last time we learned how to plot. 3, 0 means the angle is 0, the radius is 3. I'm right here, right? That also corresponds, by the way, to the Cartesian coordinate. Round braces 3, 0. What's the next one? Pi halves. Well, at pi halves, this goes away, and I'm up at 2. All right, so pi halves, there's the angle. R is 2. That's that point. How did I get there? I went this way. By the way, polar curves have a direction to them. As theta increases, you walk along the curve in a certain way. Okay, so here is 2 pi halves. If I plug in pi, then cosine pi is minus 1, and I get 2 minus 1, which is 1. Well, 1 pi corresponds to that point. By the same token, 3 pi over 2, cosine goes away, I'm back at 2. That's this ordered pair right there. Why? Because the angle is 3 pi over 2. That puts me over there with the distance 2 away. And finally, at 2 pi, cosine is a value of 1 again, and that's got me back here. I've traced out the entire curve. And this point corresponds to both the polar coordinate 3, 0 and the polar coordinate 3, 2 pi. Remember I said polar coordinates are not unique. All right. And there we have a limaçon with absolute value of A greater than absolute value of B. If you want another example, suppose instead of cosine theta, I put sine theta there. I'm going to plot it through the same points. And I start here at now 2, 0, because the sine of 0 is 0 and r is 2. So I go 2, 0, 3 pi halves, 2 pi, 1, 3 pi over 2. Because at 3 pi over 2, sine is minus 1, right? So it pinches in there. And then at 2 comma 2 pi, I'm back there again. All right? Now, we have a special kind of limacon when the absolute value of A is the same as the absolute value of B. And in which case, it does go through the origin, and in fact, it hits it, as I trace the curve one time, it hits the origin exactly once. An example of that is, and by the way, this special limacon, where absolute value of A is the same as the absolute value of B, is called a cardioid. Cardioid comes from the Latin cardia, cardiac. If you look down here, it looks like a heart. Isn't that cute? All right, so here's my example. R is equal to 1 minus sine theta. Again, I'm going to go through the same values of theta because that's where sine is biggest, smallest, and 0. So I start out with at 0, when theta is 0, it's 1 minus 0 or 1. So I go 1, 0. Then at pi halves, sine is 1, which makes r 0. Do you remember when I said whenever r is 0, where am I? I don't care what the angle theta is. I am at the origin. All right, and then at pi, sine is 0 again, so I'm at 1 pi. At 3 pi over 2, sine is minus 1. That makes r 2. So 3 pi over 2, that's that angle. Distance 2 away, that's there. And finally, at 1, 2 pi, I'm back at that point. Right? So there is a cardioid, which is a special limacon. And it happens when the absolute value of A is the absolute value of B. All right. My next example, and I think my final example for this video anyway, is going to be when the absolute value of A is less than the absolute value of B. And in that case, I actually loop inside. So I go through the origin twice as I trace over the curve. So let's look at an example like that. R is 1 plus 2 cosine theta, right? B is 2, A is 1, 1 is less than 2. So I start out with at 0, I'm at 0, 1. My curve went away there for a second. Okay, so I'm at 0, 1. At pi halves, sine of pi halves, remember, is 1. So I'm up at 3 pi halves. At pi, sine is back to 0 again, so I'm at 1 pi. Now, when sine is minus a half, that's when I'm at the pole. Where does that happen? A reference angle of 7 pi over 6, because I have to get in the third quadrant. So right here, sine is minus 1/2 at 7 pi over 6. That makes r 0. I'm at the origin. Right? And now, between 7 pi over 6 and 11 pi over 6, where I'm back at the origin again, my radius is negative. Now, if the radius is negative, so in particular at 3 pi over 2, 3 pi over 2 would be this angle, but the radius is minus 1, so it's a reflection through the origin, and that puts me there. That's where that little loop comes from, right? And then I'm back at r equals 0 at 11 pi over 6, and I'm back at 1 comma 2 pi. That's the same point as this, right? So here I trace it like that. And that is a limacon when the absolute value of A is less than the absolute value of B. I have an inside loop. If I change signs if I switch cosine to sine, what happens is the curve gets rotated, just like it did over here. It gets rotated. All right, so that is a limaçon, and I think I'll stop here.